Okay, we have acquired the data for the pulse train associated with the speed of sound in the PVC pipe. So you should download this document right here. It's an Excel file, speed of sound pulse data template. So you should download that, and then you can open it up, and it'll look something like this. You can resize it. Now, notice I've got it all fixed up for you because I want you to learn, some stuff about using Excel. I'm sure most of you have been exposed to Excel, but I'd like to teach you a few little tricks and how to make things look good and how to use it in a real efficacious manner. So basically, the first thing we need to do is, let's look at this table. Notice I've got everything labeled nice, like pulse number. That would be like the first pulse, the second pulse, the third pulse. Pulse time with units, and then notice I've got 2NLM, 2NL1, 2NL2. What does that mean? Well, LM is the measured length of the pipe. We'll write that down. I recorded it. And L1 is when you make the one-end correction, which is 0.6 times the inner diameter. Remember that? The reflection does not take place at the end of the tube. It takes place just outside the end. So the length gets increased just a little bit. And then the pipes we're using, you really should, they're double-ended. Both ends are open, so we would need to add 0.6 times the ID times 2 because both ends are open, so it would be 1.2 times the inner diameter. So, and this is kind of interesting because usually this one works the best, and we'll talk a little bit about that, why that data usually gives the best result. Okay, so the first thing I want to do is, and I'll explain how we use these variables as we go through the calculation. So the first thing we want to do is we probably should make a printout here, and I'm going to call this T. Let's see, T0, and this T1. I'll make it look good in a minute. Let's see, will that do it? Yeah, that'll do it. Okay, so notice I have that lined up here. Okay, so, and then T2, T3, T4, T5, T6. That should be enough. I think that's all I have. And then what I'm going to do is I'm going to highlight that, and I'm going to center justify it. And then I'm going to choose Roman numerals, italicize it, and then make it the same size. Let's make it about 10-point font. There we go. So these should be subscripts, but I'm going to save some time and just leave it like that. Now, let's put the numbers out here that I recorded. So if I can find that data, oh boy, I'm not ready. Where is it? Here it is. Okay. T0, our first pulse was at 20.1538 milliseconds. So we need to put E minus 3 because that's right, times 10 to the minus third. Notice it changed it. When I put 20 E minus 3, it went to 2 E minus 2. The Excel just did that by default because that's in scientific notation. So I'll fix that up in a minute. I'm going to add some significant figures there. Okay, the second one, let me go and do that now. I'm going to highlight this. Watch this. Highlight, right-click, format cells, scientific notation, and let's give it about 4 decimal places. That'll cover us. There we go. Now, see that? It was 20.1538 millisecond, but noticed it rounded off that second to the last number to a 4, which is fine. Okay, now we got 29.1538 E minus 3. So you enter that there. There you go. Then we have 38. I'm typing it just like I wrote it down. 2308 milliseconds, so it's E minus 3 seconds. Let's remind ourselves that these are in seconds. There we go. Now, the next one is 47.2308 E minus 3. I hope I'm not mistyping anything. I don't think I am. 338, 2308. Yeah, I did too. No, that's right. Okay, now 56.2308 E minus 3. T5 is 65.3077 E minus 3. And then 74.3077 E minus 3. So this is in scientific notation. Now I'm going to go on and highlight these. I'm going to make those smaller just to save space here and also center justify them. Okay, there you go. And let's put them in, let's use Times New Roman font. Doesn't seem to be consistent. That one right there. Okay, I see. Let's use Calibri. I just want to make them look the same, just so you get used to doing stuff. That's good. There we go. Now, all right, now, these are the times, like, between pulses. I mean, that's the total time. Excuse me. That's all these times are taken relative to some fixed point in the software. But what we want are difference in times. So I'm going to come over here, and I'm going to watch what I do here. I'm going to label this as Tn minus T0. So what I want to do is I want to subtract each one of these from this starting pulse. See, this really won't be included in the data. That's our starting point, and we need to subtract T naught from each one of these. Now watch how I do this. So I'm going to go over here. Right here is going to be our first data point. I'm going to say equals this number. So that's L4. See, that's column L, and this is row 4, as you can see. L4 minus, now, T naught. Now, here's the trick. T naught, we're going to subtract T0 from every one of them, so hold that static. That way it'll never change. Then when you hit that, so what you have here is the difference. That's exactly 9 milliseconds. What we have is a difference between this number and that number. That's what we just did. See that? Look up here. You can see what we did. That's our equation. And we want to hold this constant. Now watch this. When I go to the corner, it's going to turn into a skinny cross. See that? And I'm going to pull it down and get all of them. Now there you go. It updated. Now look. See how they're all about 9 milliseconds? 9, 18, 27, 36, 45. Okay, so notice what this did. We started with L4 minus L $3. And then when you go down here, you got L5, it updated, but L3 is held constant because we want to subtract, like I said, we want to subtract that number from every number. So that right there is our data. That's going to go here. That now we've labeled our pulse. That's the first pulse relative to our starting point. So what you do is you just highlight it. First of all, let's make this, I would make it small. Let's make it 8-point font so we can save space. Now highlight it, go in and highlight it. And you can hit Control-C to copy however you want. And then go over here and highlight that red column and then paste numbers. Paste numbers. There you go. Now, notice that it changed from scientific notation to standard number formatting. That's okay. There's nothing wrong with that. But these are the times. Okay, now, the next thing we need to do is we need to enter in these links over here. Here's the math. Okay, our measured length, I'm going to go over here and I'm going to put LM, and this is L1. Once again, I should be using subscripts, but I'm not going to bother just to save time. You can subscript these if you want. Just go like this right here, and then go up here and hit Font and Subscript. If you want to make it look cool, just little tricks. Nice to know stuff like that. And then generally, when you're doing math, really you want to use Times New Roman, and then italicize it. That makes it look like a book. But you don't have to do all that. But I just wanted to show you if you wanted to really make it look good. Okay, now watch what we do here. So I measured the length of the pipe. This is the length of the pipe. It was 1.530 meter. Now let's go on and put a meter up here. And notice it changed it to scientific notation, which I don't really care for this case. So I'm going to change that back. I'm just trying to teach you, so it's good to see all this stuff. Format those cells and make them number. Go to number. And then just hit number, and then we're going to need about 3 decimal places to the nearest millimeter. There we go. Now, let's look at how we do this. So this is the measured length of the pipe, 1.530 meter. Now I'm going to go in here. Now, of course, when you're doing this, you might want to stop this video so you can catch up. I'm just going to go through it. And what we're going to do is we're going to do a tabular analysis, and then I'm going to stop the video, and then we're going to come back and do graphical analysis. So all this is tabular analysis of the data. Okay, now what's L1? Well, L1 over here assumes one opened end. So what we're going to do is we're going to say equals this number. Now, it's a good idea to hold that static, but we don't have to in this case, but I'm going to do it anyway. It's just good practice. Now watch. We're going to add to it 0.6 times the diameter, and the diameter was 0.04. It was 4 centimeters exactly, about as close as I can measure. And so if I tab out, that's what you get. See that? I added that number right there is added to the length, so it's a little bit bigger. You can see it's a little bit longer. That's the acoustic length of the pipe with one end open and one end closed. Now, the pipe that we're using, really, this should be the length, but I will almost bet you that'll give better data. It always does, and we'll talk about why that's the case. Okay, now this one right here, same thing. You want to take the original length, and just for good practice, since that doesn't change, that's a static number. Okay, you're going to add to it 1.2. See, 0.6, you got 0.6 for each end, right? So that's 1.2 times 0.04, which was the inner diameter of the pipe. There we go. So that's the corrected acoustic length with both ends open. And we're going to use these numbers. So I'm going to go in here and make that 8, leave it as Calibri font. And I'm going to center justify all this junk. Looks better. Okay, there we go. So we got our units up here, meters. Everything's looking good. Now we're ready to rock and roll. So what you want to do is these are the delta times, the pulse times relative to our starting point. Okay, so this column over here is what we're going to, we've already put it over here. Good. I've already put those over there. Good. Okay, now the next thing we need to do is notice that for pulse 1, that's the difference between T1 and T0. So that would be 2NL, where N, see, I've got counters over here. That's the first round trip, second round trip, third round trip, fourth round trip, fifth round trip, sixth round trip. And you have to multiply by 2 because remember the microphone's at one end of the pipe. So the pulse is traveling down the pipe and then back to the microphone each time. So in this column, now we're going to use the measured length here. So equals, now watch what I do. I'm just going to click over here. That's our counter, our pulse counter. A4 times, right, this number. Now, you could just type that number in, but I'm just teaching you Excel tricks because this is useful if you're doing a lot of analysis. That's a static value. I need a static dollar sign, right? 2N. Whoops, I forgot my 2. Sorry. 2 times the counter, the pulse counter, times the length. Boom. Now, you can just pull that down. See, watch. You can pull that down. Why does that work? Because I'm holding the length constant, this, but when I go down here, now we're going to multiply by this. See, that's 4 links. See, we got 2 links here. 2 round trips would be 4. So 2 times A5 is 2, that's 4. See that? So this would be 2 times the length of the pipe, 4 times the length of the pipe, 6 times the length of the pipe, and so on and so forth. See how I did that? Basically 2N, where this is N right here. Okay, now we're going to do this one. Same thing, except instead of using this length, now we're going to use this length. Okay, whoops, something didn't happen there. It messed up. Plus N14. I don't know what I did there, but that should be plus, that changed somehow. I must have dragged, let's see, 0.6 times 0.04. I messed up. Whoops. I messed up here. What's going on? There we go. Sorry about that. There we go. That's good. Now that's right. Now, we got that number right. Okay, now go in here. Equals 2 times our pulse counter times this number. And then put a dollar sign in front of it. We don't want that changing when we drag it down, right? Okay, there you go. See how it's a little longer? Okay, pull it down. There you go. That's the length that the pulses are traveling. See? The first pulse travels 2 lengths of the pipe. The second round trip, that would be 4 total lengths, 6 total lengths, and so on and so forth. But the length's 1.5. Okay, now, roughly. Now, the next, we're going to do the same thing here. Equals 2 times pulse counter, N, times, okay, this, and make it static. That's our double opened in correction. And then, okay, there you go. Okay, now there you go. Okay, we're done figuring out how far those sound pulses had to travel for 3 different assumptions: the length of the pipe, 1 opened end, and 2 open ends. Now we got to measure the speed. How do we do that? Well, we just divide length by time. So this is equal to what? the yellow, I got it color-coded. It's equal to this divided by time, length over time, meters per second. See the units? Boom. 340 meters a second. That's pretty close, but the length's too short. That's why it's a low number. Okay, what do we do here? Now we're going to divide the one-end correction by the time. So equals that length divided by the time again. Boom, look at that. Now that's almost exactly right. There you go. Now this one, so in this case it did act like a one-end open. Equals, now we're going to divide the double end length and divide by the time. There you go, and that's too high. So boom, but they're pretty good numbers, all of them. Now, so there you go. There's your table, your tabular analysis of individual calculations. Now, let's get the averages. It's just learning how to do stuff here. So I'm going to say equals average, open up parenthesis, take that one. Now go to the corner and look how it turns to a little double arrow there, and pull it down and grab that population, close your parenthesis, tab out. There you go. Okay, let's average this one. Equals average. Boom. Pull that down. Boom. Okay, let's average these. Average. And then get double corner, pull it down. There you go. Now, let's do the standard deviations. Equals STDEV. Okay, grab the population. Pull it down. Boom. Okay. Equals standard deviation. Then grab this is the entire. Now don't use the average in your standard deviation, just the population of data. This is your population of data. This is your data up here. Okay, equals standard. It's STDEV. Sounds like something you don't want. All right, there we go. Boom, boom. There you go. Whoops, something happened here. STD. Oh, I see. I didn't spell it right. Right, there we go. Whoops. Okay, it does stuff like that to you. So back up. There we go. Got it. Now. Here's how you should do this. I generally tell you all to keep one significant digit in your standard deviation. That's kind of like an error. So that tells you your error is in the 0.1 spot. So make it 339.1, round it off, and write plus 0.5. Now you can go in here and highlight that plus and underline it, and it looks like a plus minus, right? Isn't that cool? All right, so here we got 0.5. There's an uncertainty of 0.5. So 344.4. See, the standard deviation's in the 10th spot, so we need to keep a 10th here. That's called precision. Plus 0.5, and then I'm going to underline that puppy. There we go, make it look good. And then we go in here and we say equals, okay, so this number here, that's that result, 349.8, round it off, plus 0.5, and then underline the 0. And we are almost done. Okay, something happened here. Oh, I know what I did. I didn't need that equal sign there. Oops, sorry about that. There we go. You don't need an equal there, right? It'll do math for you. We don't want to do math. We're just putting a number in there. Okay, there you go. Now, let's make these look good. So I'm going to, let's leave them 10 point. That's cool. That's good. Let's just center justify them. That looks good. Okay, now, what I want you to do is pick the best one here. So I guarantee you that's the best one. But let's see what the speed of sound should be. So if I go over here and put temp, and the temperature of the room, when I looked at it, was 71 degrees Fahrenheit. So, I'm going to raise that up just so you know it's a degree here. Font, superscript, up. There we go. So, but we want Celsius. So, whoops, it didn't do it for me. Why not? Why didn't it? There we go. 71 degrees Fahrenheit. So what I'm going to do is I'm going to go to, here we go. I got it open. Okay, so 71 degrees Fahrenheit. Okay, so we should get 344.6. Should be what we see that. I just put it in this. You can go to hyperphysics. There's a link in it's in that Excel document, tell you where to go. And I've got an equation here. I'll tell you what, let's use 21.7 here. See that Celsius degrees right there? I'll show you how to do it with Excel. The equation's right here. So if we use that equation, the accepted value is 331. Well, excuse me. What was that temperature again? 21.7 Celsius. So let's use that. 21.7 Celsius. Okay, now if we do that, here's the equation that I just showed you from that website. So if I go in here and say equals 331.4 plus 0.6. It's odd that 0.6 is the same as that correction, but that's got nothing to do with each other. That's just weird. All right, times temperature degrees Celsius. What's the temperature degrees Celsius? 21.7. It won't be exactly the same as the other. There you go. And what do we get? 344.42. Now look at that. That's just pure luck. It's almost perfect agreement there. Look at that. It acted like a single open-ended pipe. So that's your best data according to the table. See that? Okay, so there you go. That's your accepted value, and we only need 1 sig fig because we're not that accurate. So let me go in here and take this, and I'm going to right-click, format cells, and go to number, and knock that down. Let's see, number, and just use 1 decimal place because that's all we're accurate to anyway. And as you see, if we do that, we have exactly perfect agreement. Of course, with that 0.5, you could have been off, up from, like your upper bound would have been 344.9 and your lower bound would have been 339.9. As you can plus or minus, that's an uncertainty. But anyway, that's just really weird. Perfect agreement. Now notice, really though, that's really how the pipe should behave, which that's not bad. Even if we use that data, it's a percent off. But I suspect that the reason this is so common when you're doing this experiment, I think the pulse travels so fast when you hit it with that Scotch-Brite pad or a mouse pad. I don't think the pad fully comes off the pipe, and it's like the first few pulses actually get rebounded from a closed tube. And we would have to take data with a high-speed camera and actually see the process of striking the end of the pipe to justify using a double opened end. I know one end's open, but when you strike the pipe, it kind of acts like a closed end because you're doing it with your hand and you're not that fast. I mean, that speed of sound's fast. So by the time the first pulse comes back, the pad might still be on the end of the pipe. So that's my hypothesis for why it acts like a single-ended pipe. But look at that. That's beautiful. So we just measured very accurately the speed of sound. Okay, this concludes the tabular analysis. I'm going to come back with your graphical analysis because this video's gotten horribly long at this point, 23 minutes. It's ridiculous, but I'm just trying to hopefully you'll get some Excel and make everybody should be able to get 100 on this assignment. I don't want you to write a report. I just want you to finish up this Excel document, make it look good, and learn something. And keep it. You'll have this to look at to know how to format and stuff. And I'll do some extra formatting in the other when I open up the next video. So we will clean this up a little bit. All right, that's it. Bye.